Hempel's ravens presents a fascinating challenge to our understanding of inductive reasoning in science. The paradox arises from the idea that observing non-black, non-raven objects can somehow bolster the hypothesis that all ravens are black. This notion clashes with our intuitive grasp of evidence, as we tend to believe that only relevant observations should contribute to confirming a hypothesis. The implication is unsettling. If every non-black object supports the raven hypothesis, then our methods of verification may be flawed. This paradox forces us to reconsider the nature of scientific evidence and the criteria we use to validate our theories. It underscores the complexity of scientific inquiry, where the lines between relevant and irrelevant evidence become blurred or red. Ultimately, Hempel's paradox invites us to reflect on the foundations of scientific reasoning, urging us to seek clarity in how we interpret data and the assumptions that underpin our conclusions about the natural world. The tale of the spherical cow humorously highlights a common pitfall in scientific modeling: the allure of simplification at the expense of reality. When physicists proposed a vacuum-dwelling, perfectly spherical cow to optimize milk production, they inadvertently showcased how models can become detached from the very phenomena they aim to explain. While these mathematical constructs can yield elegant solutions, they often gloss over the complexities of the real world. For instance, assuming the Earth is a perfect sphere ignores its equatorial bulge and varied topography, which are crucial for navigation and climate modeling. Similarly, treating electrons as point particles overlooks their wave-like behavior, which is essential for understanding quantum mechanics. In astrophysics, modeling stars as uniform spheres may simplify calculations, but fails to account for their diverse structures and life cycles. Ultimately, while models are invaluable tools, they serve best when grounded in the messy, intricate reality they seek to represent. The thought experiment of the invisible dragon in the garage serves as a profound reminder of the necessity for skepticism in our understanding of the universe. If we cannot observe, measure, or test the existence of this dragon, then its claim becomes meaningless in a scientific context. This principle of falsifiability is crucial. It reminds us that for a hypothesis to hold value, it must be open to scrutiny and potential disproof. Similarly, Skinner's pigeon experiment reveals how easily humans can fall prey to superstitious thinking. The pigeons, rewarded at random, mistakenly associate their behaviors with outcomes, a phenomenon mirrored in gambling psychology. Gamblers often engage in rituals, convinced that specific actions will influence their luck, despite the randomness of the game. Both examples highlight the importance of critical thinking and the need to distinguish between genuine causation and mere coincidence, urging us to seek evidence and remain vigilant against unfounded beliefs. The infinite monkey theorem and Buridan's ass both delve into the complexities of choice and randomness, yet they approach the concept from different angles. The theorem, with its whimsical premise of monkeys typing Shakespeare, challenges our understanding of probability and the vastness of infinity. It suggests that, given enough time, even the most improbable outcomes can occur, igniting curiosity about chance and the nature of existence. Conversely, Buridan's ass presents a more somber reflection on decision-making. The donkey, paralyzed by indecision between two identical options, serves as a cautionary tale about the paralysis that can accompany choice. In a world filled with endless possibilities, the struggle to make decisions can lead to inaction and missed opportunities. Together, these concepts remind us of the delicate balance between randomness and choice, urging us to embrace the unpredictable nature of life, while also recognizing the importance of making decisions, however daunting they may seem. Rubber duck debugging is a fascinating technique that highlights the power of articulation in problem solving. When programmers explain their code line by line to an inanimate object like a rubber duck, they engage in a process that forces them to clarify their thoughts. This seemingly simple act can lead to profound insights, as verbalizing the issues often illuminates mistakes or oversights that might have gone unnoticed. The rubber duck becomes a silent partner in the coding journey, encouraging a deeper level of critical thinking. By breaking down complex problems into understandable segments, developers not only enhance their comprehension of the code, but also cultivate a habit of meticulousness that can improve their overall coding skills. This method underscores a broader lesson applicable beyond programming. Sometimes, the act of explaining a problem can be the key to unlocking a solution, proving that clarity of thought is essential in any field of work. Ada Lovelace's assertion about machines serves as a poignant reminder of the limitations inherent in artificial intelligence. While today's AI can mimic creativity by generating art and writing, it fundamentally lacks the independent thought and emotional depth that characterize human creativity. Lovelace's analogy of the horse highlights this distinction. A horse can run swiftly, but cannot innovate or dream. This raises essential questions about the nature of intelligence itself. Simultaneously, Zeno's tortoise paradox challenges our understanding of motion and infinity, illustrating how logical frameworks can become entangled in contradictions. Just as Achilles can never quite overtake the tortoise due to the infinite distances he must cover, we find ourselves grappling with the infinite complexities of defining and measuring intelligence, both human and artificial. Together, Lovelace's insights and Zeno's paradox encourage us to reflect on the essence of creativity and the boundaries of human understanding in an age dominated by technology.